Okay, this is going to be our sixth and final video on electromagnetic induction. In this video, I'm going to be discussing Maxwell's equations, and this corresponds to the end of section 29.7, which is what we started in the previous video. Okay, so like I said, in this video we're going to be talking about Maxwell's equations for electromagnetism. And so let's get right into it here. So as I say here, we're now in a position to collect all the equations that we've developed describing the relationship between electricity and magnetic, or electric and magnetic fields and their sources. And so collectively we call all of these equations Maxwell's equations. Although he's not the one that developed all of these sort of single-handedly, we'll see that we recognize a lot of these equations, and we've sort of discussed where they came from along the way. So we're going to write down all these equations for charges and currents in empty space, like we've developed them. Okay, so we've always been talking about doing these calculations in a vacuum or something similar to a vacuum, where we have our electric constant being the value that it is, and we're not doing the calculations in the present of either some large magnet, some large permanent magnet, or through some sort of a dielectric, right? Which we didn't talk about in this course, and so we don't have to worry about that. But if we were to talk about these equations in the presence of dielectrics or large permanent magnets, we would have to modify these equations. But for free space, which is where we've been doing our calculations and where we're going to talk about Maxwell's equations, this is the way these equations would look. Okay, so without further delay, here are Maxwell's equations, and a lot of these will look similar or familiar to you, I should say. The first two laws here involve an integral over a closed surface, right? So we're going to recognize the two of these right away. The first one is Gauss's law for electric fields. This equation here, is my pen working? Yep. This 29.18, and this equation tells us that the flux of electric field through a closed surface is equal to the charge enclosed by that closed surface divided by our electric constant, right? The second equation here is Gauss's law for magnetic fields. We didn't have a chance to use this one very much. There's not a lot that we can sort of do with it, because it doesn't really tell us much outside of the point that there are no magnetic monopoles, right? So we take a look at this, and we see Gauss's law for magnetic fields, and it tells us that the flux of magnetic field through any closed surface has to be zero. And if we remember back to the discussions, this is because we cannot have any magnetic monopoles. We can't have a source of magnetic field sitting inside our closed surface, right? The second set of two laws here involves a line integral around a closed path. Okay, so the third law that we're going to talk about here is Faraday's law, which we talked about a little while ago, which states that a changing magnetic flux acts as a source of electric field, right? And if we remember, this line integral has to be performed over a stationary closed path, right? So we remember we kind of had Faraday's law originally that applied everywhere, and then we made some modifications, and now this version of it only applies where we're talking about doing this line integral over a closed path that is stationary, right? And then we also have to remember that the electric field produced by this changing magnetic field is a non-conservative electric field, right? So there's some distinction to be made there. But when we do the calculation in practice, we're not going to find that we need to worry about that distinction, generally speaking. Okay. So that's Faraday's law. That's the third of Maxwell's equations. And the fourth of Maxwell's equations is Ampere's law, where we include our displacement current term, right? We can see our displacement current term over here. It states that both conduction current and displacement current can act as sources of magnetic field. Okay, and we can see that this entire collection of terms here, this is our displacement current as we wrote it before, right? And in essence, our displacement current is just the time rate of change of our electric flux scaled by the electric constant here, right? So we have Ampere's law here, right? And so one second, have I forgotten to copy some notes in here? No, I think we're fine. I wasn't sure if I wanted to say something else about these, but I think in the end I decided not to. Okay, so we're fine here. We'll continue along now. So we've stated Maxwell's for equations here, and we're now going to point out the sort of symmetries in Maxwell's equations if we're in empty space. Okay, so if we're in empty space, there is no free charge, there is no current. So let's take these equations. We're gonna set all of the currents to 0. We're gonna set IC to 0. We're gonna set the free charge here, the charge enclosed to 0. And if we do that, we can see another very nice symmetry sort of emerging from Maxwell's equations. We can see the way that basically these equations all are just restating or recasting E and B in different roles, and you end up sort of finding the same thing in the end, up to some constants and some minus signs, right? So we sort of see this nice symmetry emerging. If we take these two last equations here, these equations that come from Faraday's and Ampere's law, and we substitute in for these expressions for our fluxes, for our magnetic and our electric flux that we have here, we see that we have these two equations emerging as well. Okay, and again we see the symmetry between the roles played by the electric field and the magnetic field, right? They're almost interchangeable in the two equations up to minus signs and a couple of constants, right? And the key thing to note about these equations is that a time-varying field of one kind, right, produces a field of the other kind. A time-varying field of one kind produces a field of the other kind, right, in both cases. Okay, Maxwell recognized that these relationships predict the existence of what we call electromagnetic waves, and that these electromagnetic waves would propagate in space. Okay, it's these electromagnetic waves that provide the physical basis for all of the electromagnetic spectrum that we see in nature, right? So everything from radio waves and microwaves through visible light, all the way up to X-rays and gamma rays, right? And it may not be immediately obvious on inspection of Maxwell's equations, so we only really have these four equations. And so by looking at them, it may not be immediately obvious, but from Maxwell's equations, we can derive all of the basic relationships of the fields and all of their sources, right? So we can go back through and we can derive Coulomb's law from Gauss's law. We can derive the Biot-Savart law from Ampere's law, and so on, right? We can derive the force expressions, the expressions for electric and magnetic forces by combining different ones of these equations together. So we're not really going to go through and carefully show how you can derive these from one another. It's in practice much more useful to try to remember how to use, say, the Biot-Savart law on its own and not have to rederive it directly from Maxwell's equations every time you want to use it. But it is definitely worth noting that you could derive all of electromagnetic theory basically from Maxwell's equations, and that's really a sort of testament to the sort of power of bringing all these equations together. Within these four equations, you see everything that we've talked about in this entire course basically so far, and of course a lot more that we didn't have a chance to discuss, right? So again, like I mentioned before, Maxwell was the one that noticed that these equations bring together all these ideas in this sort of beautiful way, and this synthesis of these ideas by Maxwell is really one of the biggest achievements in physics, and it stands on par with things like Newton's laws of motion, the laws of thermodynamics, and I list a couple of others here, like the development of relativity and the development of quantum mechanics, both of the latter ones, which came in the 20th century here, right? And so this is sort of one of the big sort of punchlines to the course here. We've built up all of these ideas, and we can now finally collect them into this nice sort of box that we can refer to as Maxwell's equations, that really kind of wraps it all up with a bow on top for us, and we can sort of move forward with this collection of ideas in our toolbox. Okay. Okay, so I think that's a nice spot to leave this chapter. So this is all that we're going to be covering from this chapter, and so I'll leave it here, and I'll see you guys in the next chapter.